Corey.
Well, 2 o'clock, we may get an opening.
Okay.
We had heavy drizzle.
I think we're on, aren't we,
Oh, yeah,
gentlemen?
I will not.
Okay, you're on.
Oh my God, we just interrupted the party. We were just about to have a drink. By golly, it is the Santa Barbara Astronomical Unit's once a week online YouTube blog. Once again, that we call the SBAU Astro Hour. Happens to be our 215th program for April 14th through the 20th, into our fifth big year of telecasting on Zoom. My name's Ronnie Herron. I'll be your host, and my friends on the screen, who I'll introduce you to in a minute, and I, all members of Santa Barbara, California's longtime astrophysics and telescope club. We get together on screen every Monday morning at 11 a.m. to explore every aspect of this exploding field of cosmology that everybody loves. If it's up there in the skies above, or down here for that matter, anything about astronomy, we're going to cover it. SBAU is supported by, and we meet at, the Santa Barbara Museum of Natural History. We're there every first Friday of the month, inside, every second Saturday outside for our nighttime star party, and you are invited. Come on, join. By golly, coming up, SBAU.org, we're going to talk this week about nothing is forever. Even stars, just like us old folks, are born, have lives, check into Samarkand, and then die. Some of them go out with a bang, as we do. Ever heard of hydrostatic equilibrium? Ooh, ever heard of Cecilia Payne Gaposchkin? We got a photo of her and going to tell you all about her. Coming up in a week, the Lyrids meteor shower, which will be affected by a waning crescent moon, leftover stuff from Comet Thatcher. M87 is both a galaxy and the supermassive black hole at the center of that galaxy. Got the first picture taken of a black hole in the center. We'll take a long, hard look at stellar interferometry. I'll get that right. Interferometry.
Good.
You can't say that, can you say VLA, boys and girls? All right, let's introduce you to the gang. Mr. President, Jerry Wilson.
Good morning.
Has
Hi,
a
Joyce.
PhD, but we don't ever call him doctor. But that's okay. And he's married to the lovely Pat Forgy. How's she doing? Miss her at meetings. She's a big supporter of mine, likes what I do. Also married to a Pat is Chuck McPartland, our outreach coordinator in front of the Ukrainian flag. He is an outrageously outreachable man in charge of all kinds of things that he's can. I guess we've lost many of the hotels, and we're going to move the Westmont night, but I'll talk to you about that in a minute. Pat McPartland is a merchandise manager, his wife, and also our treasurer. Tim Crawford checked in early. How are you, Tim? In front of a picture of a solar eclipse that he took. And his wife is Karen. Good to see you, Tim. Tom Whittemore, baking bread again.
Yep.
He really has a full life, having retired from his lab out at Westmont College, married to the lovely Maureen. And on screen, last minute, Bruce Murdoch. Longtime supporter, Bruce, married to Bonnie.
Hello.
How you doing? He's also president of the Santa Barbara Theater Organ Society. Tell you what we like to do as we go into our fifth year is start our hour with sillies. And I finally figured out the one you sent about Princess Leia and Han Solo, but I'm not sure if you'll throw that up on the screen or not. The screaming snowmen. Is that coming up,
Yeah.
Gary? All right. Gary is he's our captain of the starship, Commander Wilson. Throws up our little silly science cartoons and some thought provokers. So we'll get the hour started here with some sillies and maybe even a crazy pun from Tom Whittemore. Here we go. This one I haven't seen. Are we
About
on
half of them you haven't seen.
Okay. We owe classic Doctor Who an apology. Space really does look like a quarry.
They
That's fitting.
filmed a lot of the Doctor Who series in a quarry to make it look alien.
Did they really?
And when it first started out, people complained about it.
Is that something you can still see, or do you have to go? Was it
Oh
free
no,
on?
everything is all online somewhere nowadays.
Okay, well, if it's a streaming service, I don't get it, but if it's on YouTube, and that would
Hulu
be
will have it.
is that what's the name of the asteroid we crashed into?
No, this is a Japanese lander, I think.
Yeah.
Oh, landing on what? The moon?
An asteroid.
Oh, no, they landed on an asteroid too.
Yeah,
Yes.
before we did.
Yeah.
Twice.
How'd they get a picture? How did they get a picture of the landing?
They had a camera on board.
Several.
Okay. Okay, well, this photo was taken by a robot. Oh, surface of an asteroid. That's Paul Byrne. Can you enlarge that? Because this is all new to me. It's in two parts. Are we on board? Oh, I see. This is you sent this one. Yes, you're congratulating the astronauts on board. We congratulate the ISS crew. Successful completion of the 62nd space expedition, gentlemen and ladies. You can now return to Earth. And they say, no, thanks.
We're staying here.
We hear what's going on down there. Just as soon stay up here. Okay, now this one I like. I wrote it out. Chicxulub. It's got to be an ancient Mayan word. That's now what, Yucatan Peninsula, 65 million years back.
Yeah, the map is super washed out.
Oh, okay.
Well, that's
Math is
okay.
important.
Suffice to say, it was a bad day for a T-Rex that had a glass collection because we have the inner circle of the blast area right there in northeast Mexico, about 1,000 miles across, where everything was vaporized. The black circle next out would be the lethal blast wave. Beyond that is another yellow band, couple thousand miles across, eardrums damaged. And then the outer gray, like light blue area is where glass shatters. A lot of windows were broken back then, 65 million years ago. And then the glass collection of that T-Rex. Carpe diem coming in is what?
This is someone's cell phone re-entering the Earth's atmosphere, and he was typing the message on my spacewalk.
On my space. Oh, I see. Okay. All right. Anybody watch the ladies go into space, courtesy of Jeff Bezos this morning?
No.
Talk about conspicuous
Unfortunately, I
consumption.
saw some of it.
I got up to watch it and it had already happened, and it was 6 a.m. They did it in the middle of the dark. All right, this guy put on weight, 1990. He's next to the TV slims down, and so he gained weight, and the television from
Lost
1990.
some weight.
Okay, got it.
Slim because of lifting this thing around.
Yeah.
Oh, I see. Okay. All right. I don't know. Yeah, there's still plenty of silly stuff now. Here's another one I haven't seen. These teddy bears. Looks like Japanese anime.
The two laying on the ground says the one next to it is named Ursa Minor, which means little bear. Beautiful. They're pointing up, but they're pointing up to the two bears.
Yeah.
Yep, there they are. Heavy on the bear. Now this is a good one. The one you got to blow up here. It's Han Solo talking with Princess Leia as one of her little Star Wars droids. I guess a Jedi warrior, a little Ewok or Yoda, perhaps.
Well, this is a ripoff of Calvin and Hobbes, and so that's their son down there.
Yeah.
Their what?
Their son.
Fun.
He's
Their
always
son.
doing
That's
things
the
with-
equivalent of Calvin.
Oh,
S-O-N.
oh, okay, all right. But he's playing with a light sword, isn't he?
Yeah.
And he devastated all those snowmen.
Yeah.
And it made me think, a light sword would make a damn good shish kebab in the backyard.
No, nothing can stay on it. Cut through everything.
Did they get married in a latter version that I missed? A latter show? Did Han marry Princess Leia, do you suppose?
I don't think so.
I think so.
Never forget Carrie Fisher in that bikini in front of Jabba the Hutt. That was, I think, Empire Strikes Back or one of those. Well, gentlemen, we got lots to talk about and 50 minutes to do it. Yep. So stars, we're going to start with the life of stars. We cover it all.
Yes, we are.
All right. There's a star nursery if I ever saw one. Looks like a claw from a monster movie.
These are referred to in the press as the pillars of creation.
Yep.
It's in the Eagle Nebula. The left one is in near infrared, which means it's about 1 micron off in the near infrared. The middle one is mid infrared, which is about 5 microns, and a combination of near and mid infrared. So it's a combination of the two. And this is what this is a cloud of dust in space. And you see it's got an edge to it here. It looks like it's heavily eroded, like sandstone after rainstorms. Like something is traveling this way from upper right to lower left. and it's pushing all this dust and stuff away. But where it's more dense, it's harder to push, and so it's being eroded less. And what's pushing it down here is that some stars have been created in this nebula, and they're hot young stars, and they're putting out a stellar wind, like our sun puts out a solar wind of radiation and particles and photons. And that is the windstorm that is causing this shape to be really streamlined. And it's forming in the areas where it's resisting, mostly in the tips of the fingers and stuff on this. That's where the dust is dense enough that it's being pushed together, not just out of the way. And it's starting to collapse into stars in these things. So you're going to get planetary disks and protostars up here. Here's one. Now, these stars are probably in front of this thing, but this one is suggestive that it might be right in that fingertip, but probably not. These things, these fingertips, the finer ones will form Bok globules, which will be things that individual stars will form out of. And you can tell this was taken by the James Webb Telescope because it's got 6 radial spikes here. Is that 6 or 8? 1, 2, 3, 4, 5, 6. So it's this pattern of diffraction around it that's unique to the James Webb Space Telescope.
Dumb question, please.
Go ahead.
If I was in a spaceship in the middle of any of those, I'm sure they're hundreds, if not thousands of light years across. Would I be able to see any of that stuff around me?
You would see, it's not like in a Star Trek thing where you're in the Mutaran Nebula, which is like being in a fog bank. It's nothing like that. You would see a dimming of the stars around you, but you wouldn't notice that you're in a cloud with vacancies whipping by you like an airplane going through a cloud. It's from a point of view of a spacecraft, it's very tenuous.
Well, do you suppose it's just as thick as the stuff that would be in our heliosphere? You know, all the solar wind from the sun goes out and there's a border. It's like a bubble that's created. Yet we don't see those bubbles in space around.
It's a similar effect, but our star puts out a very weak solar wind compared to what's going on here.
Oh, is that right?
These are very hot young stars that are producing that glow.
Yeah, up and to the right, there's a cluster of brand new, very hot stars.
Yeah.
And all that stuff came from stars that blew before, so they got the higher elements beyond.
That's exactly right. And that's the point of this little topic here, is that you start from dust, you make stars out of it, the stars burn through them, their fusion processes, different elements, and depending on how much mass was together, they either slough the outer layers off, creating dust again, or they blow up completely, producing a lot of dust. And novas produce a lot of water when they do it.
Water.
Yeah.
Those little H2O.
Now this was sparked by this graphic which I saw, which we have covered before, but it's a very nice graphic. And I know you always ask about it, Ron. So this shows that star-forming nebula, which we just saw as the pillars of creation. Right. And we're traveling around this way for the first try. But whether you go this way with a little mass or you go this way with a lot of mass is just happenstance of how much mass is glomming together by gravitational attraction eventually. But the process is started by some kind of shock wave going through or stellar wind blowing through that pushes all this stuff, starts the condensation process. And then here's a protostar, which is at the tips of those fingers eventually. It produces a sun-like star at this medium to light mass ratio. Then after billions of years, it turns into a red giant. So this is where we are now in our sun, about halfway between here and here. So it's about 10, for us, it's about 10 billion years here. And we're at about the 5 billion year point, roughly. So someday it'll be red giant. Maybe it'll absorb the Earth in its orbit, or maybe not. That's debatable. Because the sun will definitely get real big without exploding. It'll just grow. but it'll lose mass in doing the process, and it might lose enough mass that the Earth's orbit expands enough to stay ahead of it. Or it might not, and it might get absorbed into the sun. We'll have to wait around and see.
Are there basically three generations of star formations, and we're number one? They do them backwards. I think I remember us
Yes,
talking
that's
about.
a different topic. This
Oh,
is
it is?
yes, we're population 1 stars, which is the most recent stars. Population 2 is an earlier one, and population 3 is the very first one, so just hydrogen. But this is the same diagram for any generation, any population of stars.
Oh, I see. Either one.
Yeah, this
Except,
one, for population 3 stars, it would be all hydrogen here. And
So
then
they
you
would-
get, but then it would produce other elements. And then when the planetary nebula forms, it throws out the dust that it has, its outer layers, and you get a white dwarf from the core right there. And the dust goes out to contribute to a cloud to be born into other future stars now with more metals in them. The other one is if you can get you can get a crowd of dust real excited and get them all together, then you can produce a massive star. And that becomes a red supergiant. And there are some really big stars out there. And those things end up in a supernova. The supernova produces all this dust and gas and chemicals and molecules and atoms that it blew out, which contribute back to the dust for new stars. And it creates either a neutron star, or if it's heavy enough, it creates a black hole.
And this is one of our handouts that we give out, except we have a black and white version to save on the printer ink.
Right.
well, there's all kinds of other things that are created that I wonder where they come from, like magnetars.
Those are all
That's a
special
neutron star.
cases.
That's a neutron star with a heavy electromagnetic draw or spectrum or whatever you want to call it.
Mm-hmm.
Hmm.
Magnetic field, no one has found yet a magnetic monopole yet, although many theorists are jumping up and down saying, no, it has to be. But no one's found one yet. So the only way we know to produce a strong magnetic field is to take electric charge and have it spin in a circle. So it's spinning around. So a highly spinning neutron star that is charged will become a magnetar, because it will produce a strong magnetic field.
Huh. Okay. And it
Where,
doesn't.
where does a pulsar fit in there?
Same thing.
What?
Same thing? Yeah.
A what star?
A pulsar.
A pulsar.
Yeah.
Oh, okay.
That the one that's spinning with
Yeah.
jets going on both sides,
Yeah.
and they'll spin hundreds of times a second.
Yes, you get millimeter wave, or microwave size light waves out of it, or pulses.
So that first generation, which has got the number 3 as it counts backwards,
Yeah.
was hydrogen and helium. So there was no chance of not only life, but even planets. That you couldn't have a planet made of hydrogen and helium going around an early star, could you?
Sure you could, if it just wasn't big enough to start thermonuclear fusion.
Look at Jupiter.
Yeah.
It's all hydrogen and helium. It's got other stuff in
Mostly.
it. Mostly, is it? Okay.
Now, I always kind of get confused here with the massive star side in this image here. I read it kind of small to read, but it says it's 8 to 10 times the mass of our sun to go on this side where it becomes a supernova. Is that the Chandrasekhar limit?
No, that's where you add mass to a white dwarf and it explodes.
Oh, okay.
Add mass. Well, wait. Is that the Corona Borealis thing we're waiting for?
No, that's a
No.
different level of explosion.
Oh, okay.
The one with the Chandrasekhar limit is when it blows up as a type 1A supernova.
Boy, I sure admire anybody that can say that name.
And probably saying it wrong,
Yeah, I learned it Chandrasekhar.
yeah.
Chandrasekhar.
Yeah, Chandra is the
well-
word. Chandra is, I think, the word for moon.
He
It's Chandra.
preferred being referred to as Chandra.
Yeah.
Yeah, it means moon.
Oh boy, I like that idea.
The stars that explode as supernova are usually what? The big red giants, not our own
Not
sun.
red giants, red supergiants.
Supergiant.
Well, where do they? Okay, what's the difference? Where's the line drawn? How big does it have to get?
Right up here in this line up here. Let me
8 to
see if I
10
can-
times the mass of the sun.
Mhm.
Okay, they will go out with a bang.
Yeah.
A
Mhm.
big bang.
How will the sun do it? How will it just dissipate and go
Well,
away?
that's this circle on the left is a sun-like star.
Hey, there it is.
Yeah.
Yeah, it'll become a planetary, Ronnie.
Now, down this line, you're in, and what's your term you were going to learn this time, Ron?
No, I don't know. Give me a clue.
Hydrostatic equilibrium.
Oh, there you go. Yeah, that's
Oh,
And that's gravity pulling it in and radiation pushing it out. What happens when it runs out of fuel?
It shrinks big time.
it
It
becomes a
not only
black hole
shrinks, it collapses.
and then explodes.
All of a sudden, no, it doesn't really explode.
It bounces.
Crashes down and it rebounds. It bounces off its core.
That's not an explosion.
But that's on the supernova side.
Okay, but there's different novas. There's kilonovas, supernovas,
A kilonova is a collision of neutron stars.
Oh, it's two stars hitting each other.
Yes.
Yeah.
Has
There's
nothing to
also
do with.
there's also Nova Lox. Delicious, by the way.
Yeah.
Da, 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 da. So,
Okay.
got it.
Anyway, when the hydrostatic equilibrium disappears, then everything collapses and then rebounds. The outer layers of the star bounce off.
Well, that's not so much what happens in a white dwarf phase. That's what you see in a planetary nebula is more what came off in the solar wind as it's going through these pulsations where it's sputtering.
Yeah.
The real rebound happens in the supernova.
Well, that's a stronger rebound.
Yeah, much stronger.
Yes.
So the ring nebula was just a former, just a
Sun-like star.
Yes.
sun-like star, right?
So your white dwarfs and neutron stars just stay like that forever? What happens to them?
They cool off and disappear.
You're
They're
A
kidding.
white dwarf, anyway. It turns into a lump of charcoal, basically.
Right.
It becomes a
the
brown
fusion-
dwarf.
The
then
fusion
it
in the
goes
white
away.
dwarf has stopped. It's just white hot from its previous life. It's got a hangover now and it's going to take a while to cool off.
But I've heard some dreadful endings proposed to the universe where it's just going to fade out and go black and everything will disappear. Where the
That's
hell?
the heat death of the universe. And it was calculated by a French guy, Poincaré. And the lifestyle or the lifetime of the universe under those conditions is conveniently called one Poincaré cycle.
I think it's Poincaré.
Point
Yeah,
whatever.
right.
But
I didn't do well in French.
supposedly matter and energy can't be created or destroyed, and yet they are, aren't they? Or that's what
No.
we're
They
looking at.
they can be turned into one another.
I know that,
Both
but they never.
Two
They would never.
aspects of the same thing.
Okay.
Okay.
All right. There she
We're
is.
going to move on to the hydrogen lady,
That's Cecilia.
Cecilia Payne-Gaposchkin. This is
Gaposchkin.
from an article in Sky and Telescope magazine.
Well,
And I'm going to include a female astronomer every week for the next, including this one for the next 10 weeks.
Yeah.
Because there's a really good discussion of that. And I think it's Astronomy Magazine, and then they're doing it also in Sky and Telescope.
Yeah, Jerry, I taught with somebody at Evergreen when she was a little girl, met her.
Okay.
Yeah, just kind of
Really?
heard this person's father was sort of a world-renowned Czech astronomer. She was fluent Czech,
Yeah.
and as a little girl, she met Payne-Gaposchkin.
well, where was she? Where was she?
Gaposchkin was her husband's name. She
That's
was
right.
Celia Payne.
Mm-hmm.
Talking
So, and who was it? Eddington considered her a pain in the, anyway. So the reason we're doing this is that the science has been, in my opinion, been a
I think a
little.
lot of
hard for
people
women.
considered Eddington
Yeah.
you
So,
know what.
so we're doing it to give women their due. They kind of
That's
get
good.
neglected in science.
ladies are taking over, and I'm all for it. They launched 7 into space briefly this morning.
Those were not scientists.
Oh, I know that. I
Harry,
know, but
Yeah.
I know, but at least they were astronauts temporarily.
they were billionaires.
Yeah.
There you go.
At least they had a billionaire, but send them up.
Okay.
Okay.
Now this is the solar spectrum. This is the what the spectrum of our sun looks like. And there's a rainbow background because the sun, the body of the sun, is a black body emitter. So it emits every wavelength of light. And
I wonder what the resolution is in this. How many nanometers wide is the?
that's a
the
good
individual
question. I
part?
suppose I could look it up, but I don't know it offhand.
So this is your Roy G. Biv.
This is
Yes.
what?
Mhm.
Roy G. Biv.
Yes, it is.
Yes.
The green is in the middle.
Yes.
Okay.
You could probably figure out the resolution if you go between those two calcium lines and
Mhm.
figure that
Sodium lines
separation.
here.
Yeah.
Yeah, those are the sodiums.
Sodium.
And this is the hydrogen alpha up here. And you notice some lines are very sharp, fairly sharp, and some are very fuzzy and broad. The reason they're fuzzy and, well, first of all, the reason these black lines are there is because there are atoms in the atmosphere of the sun, but no atoms in the body of the sun. So the body of the sun is emitting every wavelength, but the atoms in the solar atmosphere are absorbing the light from below coming out of the sun. And that's why it's missing from here. And you see the black lines. Now, these black lines are fuzzy, which means the atom is very turbulently moving. And these are Doppler shifted lines. So, or they're called thermal broadening, I believe, or
Yes.
Well, that's
right.
also magnetic broadening of the lines too.
yes, there is.
Through the same on effect.
Now, is this enough high enough resolution that you're seeing what is it, Raymond? The splitting of the lines due to magnetism, I think it is.
Due to Zeeman effect.
Yeah.
Zeeman, that's it,
Zeeman.
right?
Yeah. Yeah, I believe that's part of the, I don't know if this is high enough resolution to show discrete Zeeman, but I'm sure that, as Chuck pointed out, part of the broadening is the Zeeman effect. So,
The Zeeman is also just spreads what was a single line out to a double line separated. I remember having to do that in college in an experiment.
Yep. But the key of this thing here is showing you this is the data that Cecilia had to work with to determine the percentage of each element in the sun. And that's what she did. That was her thesis, was what is the sun mostly made out of? And let me see, where's the, oh, there it is.
I wonder if she had
other
a
stars.
mask. I wonder if she had a mask with the individual lines of elements that she could lay over this and say, okay, well, that is, then things line up. So she identifies that as an element.
They did have it because we did it once in a lab I took. You have sources, gaseous sources, for example, of different elements or things that you burn, like the easiest thing to do, take a lump of sodium and put it in a flame and burn it like salt. And you can see the sodium lines real clearly. And they're bright there, they're not dark because the atom is emitting the light. Here they're dark because the atom is absorbing the light. But let's move on. This shows the different series. For example, I'm not sure I can pick out the Balmer series or the Lyman series. The Lyman series is down in here somewhere. The Balmer series is up here with this as the primary one. Then it has another line down here, and at certain distances, it has decreasing intensity of lines. And that's because it's transition from the first orbital, not orbital, and every orbital can contain 2 electrons, spin up and spin down. This is the N1 orbital, and this one can be, this is an S state, And you can get transition here. If it jumps from here to here, it's a bright line. If it absorbs light, if it falls from here to here, it's a bright line. If it absorbs light and gets bounced up here, then it's a dark line. And you can see these series. And for the Balmer series, this one here is the hydrogen alpha line, 656 nanometers, or for people calibrated in angstroms like I am, 6,560 angstroms. So then the next one, a shorter one, shorter one, shorter one. And there's a whole series of these. They got onto this and started looking for different lines. This is in the visible red. This is down closer to the blue and green. And then you can go into the ultraviolet for the Plashan series. And
Jerry,
people started figuring this out and rushing to get their name on a series.
Yeah, if I could interrupt.
Go ahead.
Yeah, the D lines are pretty easy to see in just a lab spectrometer. It turns out they're separated by about 6 angstroms, 0.6 nanometers. Okay, so that'll give you a scale set for your picture.
Okay.
Okay, if those are in fact the D lines, I'm sure they are because they're yellow sodium.
For the benefit of those of us who don't know, is the angstrom have something to do with the frequency of the light?
It's a wavelength. It's
wavelength.
a distance measure.
Wavelength. In other words, the upper part of that screen is a lower frequency than the bottom part of that.
That's correct. Yeah, these are longer wavelengths. These are shorter.
Right.
This is higher frequency, more energetic.
And most of the lines on that previous view graph that you had are ultraviolet and more, like 410. You can't see it, 434 or 486.
Right.
Huh.
And all the ones on the upper one you can't see either.
When I was in college, I could see the 434 with my eyes.
Yeah.
I can't anymore.
Yeah, pretty soon you have kids running around to each other's table and saying, "No, I can see it here." And they look in there and they can't because everybody's eye is different.
Did Cecilia come up with all this?
No.
He used this as a tool. This was spectroscopy, and I believe it was developed about 100 years before, in the late 1800s. And she did this stuff in 1920. This is her thesis, 210-page doctoral thesis.
Yeah.
Where Otto Struve, famous astrophysicist from the 50s and 60s, said that hers was probably the most important thesis ever written in astronomy. And here, before she was married, these are the abundances of that she calculated from her work with the spectra, atomic number, hydrogen, helium, and this is a log figure. So this is 10 to the 11, 10 to the 12. That can't be right. It's got to be the other way. So helium is, well, no, helium ion. Okay.
So it's log A. Oh, you were right.
Ion means an extra neutron.
No.
No.
You're
That's
missing
isotope.
electron.
Oh, thought there was 2 of each. 2 protons.
There's 2 of each in each orbital, but the orbital might be populated with 1 or 2.
Well, Jerry's talking about electrons. Ron is talking about protons and neutrons.
Oh, yes. Sorry.
Well, there's 2 of each, though. In a helium atom, there's 2 protons orbited by 2 electrons, right?
No.
And 1 of each in a
well,
hydrogen.
2 electrons, yeah.
So what
It's
makes
a
an
simple-
ion?
Well,
It's a
wait, if you
simple
only have 1
atom
electron
that you
out
have.
there, or
Really?
none.
Somehow you get an atom with 2 protons in the nucleus and 1 electron around it?
Yeah, that's an ion.
That'd be an ion. So it's
That's an
lost an
ion.
electron, Ron.
I've
The
never heard
charge
that.
is not balanced in that case.
Wow.
You need to have equal number of electrons and protons for the charge to be balanced.
But they got to be smashed together in the bowels of a sun to become many, many orbits. Early in the creation of the universe, none of the big elements got together in large atoms,
No.
multiple layers. They all just stayed 1 or 2 hydrogen, helium.
Yeah.
Interesting.
A little bit of
Well,
lithium
the
and
first-
beryllium.
The first supernova sequence, way back when, out of the first generation of stars is where you're going to get things that are higher than lithium.
Yes,
The protostars, the stars that formed initially, are hydrogen, helium, and I think a little bit of lithium.
yeah. That's the mantra.
Wow.
Okay, so this is Henry Norris Russell. He's a very noted astronomer at that time in the 20s. And he passed away in 1957. He's considered a formidable figure in astronomy during the early 1900s. And he was initially a skeptic of Payne's results, especially concerning the composition of stellar atmospheres.
Is that device with him in the picture a telescope?
No, it's a
No.
it's a plate, a microscope for looking at plates.
You
Photographic
can
negatives.
measure the separation of lines when you put an astrophotograph in there, the negative.
Yeah.
Okay, got
And
it.
the micrometer thing that you have to see over there on, as I look at it on the left.
Yeah. So he talked her into putting a line in her thesis that
Oh, yeah.
was very painful for her to put in there. The outstanding discrepancies between the astrophysical and terrestrial abundances are displayed for hydrogen and helium. The enormous abundance derived from these elements in the stellar atmospheres is almost certainly not real. So even though she correctly derived the abundances, it went against the dogma in astronomy at that time. So he talked her into putting that in there, which was a major mistake.
And it took him a while to admit that.
Yeah.
That's right.
I was going to ask if he ever gave her any credit at all.
Yeah.
No.
I don't know. Good question.
Right. Tim, there's a phrase for that. He was full of himself.
Yes.
Oh yeah, I saw Shapley's name there as editor. I'm wondering how he was involved in
He
it
was a
all.
little kinder to the women who worked in that observatory.
Yeah, Harlow.
Russell never was.
Okay, I probably have those backwards. I remember you talking to me once about Shapley and said that in a way he was a little bit rough too.
Yeah.
That's a rough
Oh yeah.
edge.
Oh yeah. I
In
think
science, we refer to that as being pretentious. The
Okay.
person's personal opinion is more important than someone else's data.
Yeah.
They're also known as a pinta.
As a what?
Pain in the.
Oh,
Oh.
yeah. So this is a very nice composite picture of our Milky Way. And she basically pinned down the abundance and compositions of all the stellar atmospheres,
Wow.
stellar surfaces. And to her credit, these are the large and small Magellanic Cloud in the southern hemisphere.
Wow.
This is looking up into our northern hemisphere, and this, of course, is the central bulge of our galaxy with the core in there and supermassive black hole.
Yeah. Is that just an SLR, Jerry? That's just really pretty. Just a camera looking up.
It's a mosaic of multiple
mosaic,
pictures.
Yeah.
Multiple pictures that are pasted together in like Photoshop.
Yeah, but not a telescope, probably.
No.
No, just camera.
No, I think just normal cameras at the size of it. Yeah,
Really pretty.
very dramatic.
Somebody who spent a whole year doing it probably too to get all of that.
Yeah.
And traveled to the southern hemisphere.
Yeah.
And right in the middle, you can see the Pipe Nebula.
Yeah.
Stands
What,
right out.
This
Right
year?
there.
Yeah.
Huh,
Or the
okay.
emu, if you're in Australia.
And here's the Rho Ophiuchus complex.
Yep.
Ophiuchus is in the middle.
Yeah, watch your tongue, Ron.
I'm sorry.
Yeah.
That's the one house in the zodiac that gets no respect.
Okay, now this is coming on the cusp between this week and next week. This is the Lyriad meteor shower. It's going to peak on the night of April 22.
Okay.
And next Monday is April 21. So that would give us very little advance warning. So I decided to include it here because it is broader than that. And so you can start looking the weekend before the 21st and possibly see Lyriad meteors. They are the
Called a Lyrid because of its radiance.
yeah,
Yes.
Where,
Yes, in Lyra.
this is Lyra right here, which is the constellation
Okay.
they're named for. But the radiant is in here or up here. It's up in this part of the sky. But you'll see the meteors around here.
Mhm.
And of course, the predicted peak is in daytime for us.
Yes, but
Yeah, always.
it'll be at night too. This is at 1 o'clock in the morning on April 21st, the about 10 hours before our show next Monday.
Mhm.
Is this
So,
Greenwich Mean Time?
It's Universal Time.
Yeah, same difference.
Oh no, this is our local time up
That's
here.
us.
Okay.
That's us.
Yeah, that's us. The predicted peak is at 1600 hours Universal Time on April 22.
So that's 9 a.m. for us.
and the comet that left its junk behind was called Thatcher.
Yes, Comet Thatcher, which is on a very long orbit.
Is it going to come back?
It is going to come back, but not in anyone's lifetime that we know.
Okay. I'm sure we've covered this before, gents, but do we go through the tail stuff of Halley's at all?
Twice.
Yeah.
Twice? Twice a year?
We get 2 showers from that. Yeah. The
And what-
Orionids in
what is-
October when we usually have our camp out, and 6 months before that, so sometime in April.
Did you say Orionids?
Yeah.
So that's where its radiant is up in
Yes.
Orion.
Yeah.
Okay, got it.
So this is I don't know the exact date it's from, but this is years ago. This shows what is considered typical of the Lyrid meteor shower. It has a lot of large fireballs in it, or bolids. The thing that distinguishes those is they leave a persistent tail in the sky after them that fades from orange to yellow and then goes away. So they're quite dramatic. This is a composite of meteors seen one night. This is Lyra here with its trapezoid and Altair right there. And this is the radiant right here. If you draw a line back, they all converge on one point right there next to the constellation of Lyra. And this shows a plot of the April 22, 2018 orbit of Comet Thatcher and the Earth passing through the stream of bodies. These tend to be larger objects than we normally get, and the meteor shower is more dramatic because of that.
Can I ask my dumb question, please?
Go ahead.
Why does all that stuff stay stuck behind? Why isn't it still moving with the comet? The comet's moving. It doesn't
It is.
matter how big anything is, right? Why doesn't it continue on the same track the comet went on?
Well,
Because
it
it
is
has a
that
velocity.
the track is right there. Oh, I'm using my finger. You can't see that. The track is right there.
I know, but if we keep running through the tail that was left behind, why isn't the tail still moving?
It is.
It
It's
is.
moving in that orbit.
They're all of them obey Kepler's laws.
Okay, so all this stuff is not just stuck in a certain place that we pass through. It's an actual moving trail of that track the comet took, and we just happen to cross it every year.
Well, it's stuff the comet burped off that's still in its orbit.
Yeah.
Yeah, it's like a donut of stuff moving around in there, and we pass through the donut. We don't hit the same stuff every year, but we
Okay,
hit the donut in the same place every year.
I see. Okay. Because down here on Earth, if something fell off a moving vehicle, there's a friction and the gravity stops it.
The air slows it down and it stays where you threw it out.
Exactly. That doesn't
If these
happen
were
in space.
cometary particles, they would follow your car forever.
Good. That explained it. Thank you, gentlemen.
And they're affected by things like the solar wind that kind of pushes them out a little. So that's why you end up with a big donut that gradually dissipates.
This comet was discovered in 1861, around its last perihelion, and it has a period of 415 years. These
Wow.
particles that are shown here enter the Earth's atmosphere at around 102,900 miles per hour. So
Jeez.
these are really moving.
We sent a probe out to bring some of that stuff back,
Not
didn't
this
we?
one.
A little mesh screen.
That's the one that had the aerogel.
Oh,
Yeah,
yeah.
what's the biggest item that would come off a comet? A piece of sand, like a grain of
The head
Well-
of the comet.
well,
Yeah.
if that sucker lands here, well, that's the end of it. There goes our glassware
That's
again.
actually prophetic in the sense that the most dangerous thing for collision is not the asteroids that we're measuring, but comets, because comets will suddenly appear in the sky. And if one heads right for Earth, we don't have a lot of time to prepare for it. But with
Yeah.
asteroids, we can track them a long time in advance.
We can't track comets?
No,
Why
they
not?
don't. They just pop up. They just come in all of a sudden, one
Come
time
in out of
around.
the Oort cloud, huh?
The nice thing about most asteroids is they're sort of in the plane of the solar system. So that limits the area you have to look for them. But with comets, they can come from anywhere.
But that one that wiped out the
didn't know
dinosaurs
that.
65 million years ago, that could have been a comet instead of an asteroid, right?
No, because they found a lot of iridium around the Earth. That was
Yeah.
one of the clues.
Iridium's not in comets, but it's in asteroids.
Right. It's much more common in asteroids than it would be in any comet.
It's not common down here on a rocky planet like Earth. It didn't get made in the sun, whatever
Well,
it is.
no, it gets made in kilonovas, but it ends up down deep in the crust.
Is it a metal?
Yeah,
Yes.
it's a heavy
Iridium.
element.
I wonder if you can turn it into something. You know, some metals, titanium, aluminum, become really important.
Well,
Iridium-
iridium is used in some things.
Yeah, iridium has a property of being almost, it doesn't have a big coefficient of thermal expansion with heat. So it was used for a long time as the international standards for length. So there was an iridium bar, a tungsten iridium bar in Paris that was the universal standard of the meter. There were two marks on it that were 1 meter apart. And for a long time, that was the standard of the meter because it was not very sensitive to temperature change.
But there's a layer of the stuff all over the Earth, isn't there?
Yes.
Yeah, it's not a layer that you can mine. and make
Okay,
money
but
at.
it helped us determine that 65 million
That's right.
year date, didn't it?
Yeah.
Wow.
That's the
Here's-
KT boundary.
So
Yeah.
anyway, go ahead. Well, we're going to shift gears now to interferometry.
DLA.
Yeah, this is the very large array in Atacama.
Atacama, New
Alma,
Mexico.
in
New Mexico.
Atacama,
Oh, no, this is down in Chile then.
yeah.
Yeah.
And this is the Andromeda Galaxy over here.
Hmm.
So
Okay.
these arrays do synthetic aperture telescopes. So the distance between the receiver on this one and the receiver on that one the signals from these two can be combined in a way that it acts like a single mirror of diameter that's the distance between these two. It's exactly like if you had a very large mirror in your workshop. Say you had a 26-inch mirror, parabolic mirror, and you took a piece of cardboard and you put it over the mirror with two round holes in it that were near the outer edge, the circumference of that 26-inch mirror. So they'd be about 24 inches apart. So you could take the signal and then you've shown it at a star, pointed it at a star. The light would come out, would hit those two holes in the cardboard, and it would reflect off the mirror and it would combine to a single point. And that's how you construct the image from two separate apertures, but you want to combine it into one signal. The only thing and then with the mirror and the cardboard over it, the things are already lined up and phased, so you're getting the same phase of the light going up to produce the image. But when you do it with telescopes, with different radio telescopes, you measure the signal here, because these are radio waves now, which is exactly this, they're photons. So the signal here hits first, and the signal from that object here hits later. and you have to correct the timing of the signal so that by this delay time, by the distance between the two telescopes and the sign of the angle of where you're pointing to. And so that you don't have to do that with your big mirror and the cardboard. But now to combine these two electronically, you have to very accurately time the signal. You have to delay this signal so that when you combine it with this signal, they act as if they came from a single surface. And that's how you get them to act like producing a point over here. Of course, they don't have the light gathering power that the big mirror has.
I think you
have
just
the
answered a
resolution.
question I've had for years.
What's that?
Is it if you separated scopes by longer and longer distances, and even to the fact where you would separate these scopes by, say, a light year, where is there a limit to what you would be seeing as far as time wise? And I think this answers it.
There's no limit in theory, but there's many limits in practice.
Yeah.
But they wouldn't have the problem if they were all pointed straight up, would they?
That's true. They'd all be on exactly the same. Then the signal they're producing is in phase, and it won't interfere.
So I was reading an article where they actually do a two-dimensional Fourier transform of the data. Yeah. That's what's transmitted.
Yeah.
That takes care of the timing issue.
Yes, there are tricks you can do that are more sophisticated to do this, but this is the basic physics of what you're doing. You're accounting for this difference in phase between the signals. There are different ways of doing it. This is the simplest one that you can think of, or I can think
That's
of.
Fascinating. That really.
And I think, and the reason we're doing this is that the very interesting talk last week, I don't think he covered this adequately. I heard a lot of people puzzled.
Yeah.
So, I mean,
and for the char array down there at Mount Wilson, where they put the small telescopes out to act as a big interferometer.
Yes.
They had all the light piped into a room where they had mirrors that would just bounce it back and forth, and these things that were like skateboards that they could move back and forth with mirrors on them to even out the travel time.
That's right. So whatever happened to one happened to the other side.
Yeah.
So they weren't radio telescopes, and they didn't do a delay on one to the other. They actually made the beams come out after traveling the same length, as Chuck said.
Oh, I see.
And this is a planetary disk seen by ALMA using interferometry imaging, false aperture in 2 dimensions. Now, when you make an image with radio telescopes, when you look at our optical telescopes, you see the image with all its pixels. And when you see a picture like this, it's made up of little pixels. You can zoom in and you can see the individual pixels are just a small square with one shade of gray in it, for example. And that's what you get out of each look in a radio telescope. It looks at one pixel at a time, and then the whole array moves to the next pixel, and you build up the picture. Now, you can also just point the radio telescopes at your object and let the Earth's motion scan it by, and you'll see this bumpy wave for signal. Then you move down a little bit, and you do it again, and you get a bump for the next line of it. So you're building it up through a raster pattern like the old TVs used to do for making their image with a cathode ray tube.
When we went to the Owens Valley Radio Observatory, myself and Art Harris, I got a lot of education there. Number one is that the radio telescopes don't have one receiver; they got 19.
Yeah.
There's a whole group of horns there so you don't get just 1 point; you get 19 points.
Well, when you do the radio interferometry, you're having all 19 telescopes looking at the same point.
Is that ever done with optical?
Yes. That was that char array at Mount Wilson that I was talking about.
So right, but the 19 receivers that you have are not precisely in the same location.
No, there's a distance between each one of them.
And they use that.
Different apertures affected.
Right.
So, but we do it when we make our telescope images, we have a camera that has a two-dimensional square array of pixels. So we're looking at each of those pixels, and when we hold it steady by having it track the sky, and we build up the light signal that comes from each one. But when we
We'll do
make
the same thing with the radio telescopes.
well, what? Say it again.
No, they do the same thing with the radio telescopes. They track. They're
They
on.
do track, yes, but they don't have a square dimensional array. They're
Oh,
looking
no,
at the whole array of antennas is looking at one pixel at one time. When we do satellite images of the Earth, many of these satellites do not have they're not built like cameras for our telescopes with a two-dimensional array. They have a linear array. A weather satellite I worked on had a 1 by 100 element array, and it was scanned over the Earth. And the reason for that was you're looking in many different bands, and the weather is moving very quickly. And so you want to get all the different colors to line up on the same feature. You don't want to take a picture of that and then a half a second later take another picture of it because something will have moved. So you want them to immediately scan right after each other, and then you put the pictures together as if it were a square array. So all you send back to Earth is the time signal for when that picture was taken and the gray level for that picture. And then you put it all back together synthetically on Earth. And that's very similar to what radio telescopes do.
And this diagram that's showing now, Ron, this is optical. And you
Yes.
can see how they have that adjustable delay line.
Well,
Yeah, this is what the telescope on Mount Wilson did with the 100-inch, except instead of telescope 1 and telescope 2, they had a mirror and then another mirror on an arm sticking out of from the top of the tube of the 100-inch, and the light hit those mirrors and then went on this journey.
well, a stupid question perhaps, but your radio telescopes are involved with the lower end of the electromagnetic spectrum, below the optical, your Roy G. Bibb, your colors. The upper part, the real hardcore, is gamma rays and X-rays. What is the devices that watch and catch those?
X-ray telescopes.
X-ray telescopes. Now, an
X-ray-
X-ray telescope is pretty tricky because, there's not much that will, X-rays pretty much go through everything, certainly go through my body. And if you put a telescope mirror that we made in our workshop, you put them up, the X-rays will go right through it.
Right, unless you have multi-layers.
Yeah.
Yeah, so what you do is you make a cylindrical thing like a coffee can with its both ends cut out. And you point that at the X-rays, and the X-rays will skim like a stone skips across the top of the water.
Right.
It will slightly reflect off the inside of that that metal cylinder. And you have a whole bunch of metal cylinders all concentric with each other, and that's the aperture. But you can't deal with high angle X-rays. You can't control them optically. You have to do this very slim glancing off of metals. And making those telescopes with accurate parabolic inside parts of the metal telescope very accurately, that's proprietary to different companies. And they don't share how they do that.
So Jerry, we were able to do normal incidence X-ray detection when we studied the sun at Lockheed Research Labs by creating tungsten carbon multi-layers.
Okay.
The X-ray photons that came in, they rattled around and then they bounced back out to the tune, I believe, with the best we did was in the 35% range efficiency.
Okay.
So you didn't have to have those slight angle designed problems, with the previous kind of telescope mirrors.
Okay.
Yeah.
I wasn't aware
Jerry,
that
can
that
I
was
ask?
possible.
Can I ask a question I'm confused on here?
Okay.
So let's say that take the example that you have here, and you've separated these two telescopes and you're combining the images.
Yes.
And that is going to improve the resolution. It will act as if the mirror is actually as wide as these two telescopes are
It will
apart.
act exactly like there's a giant parabolic mirror between these two telescopes.
Right.
and you just have holes that you're bouncing off of on the edges of the diameter.
You'll get the resolution, but not the brightness.
That's right.
Exactly.
Mhm.
Will it improve
And the
detail?
telescope
Yes.
example I gave, the telescope has to be tipped, so it's normal to the incident radiation.
Yeah.
This
Yeah.
this one accounts for the distance difference.
Yeah. So Tim, the resolution goes as the difference of those two. So it's sort of like if you have a 12-inch mirror compared to a 6-inch mirror, the 12-inch mirror will increase the resolution power by a factor of 2.
But
Okay.
only in one dimension.
That's right.
I'm just a little, the more I think of it, the more I'm a little bit confused because I can't see how you're getting the same amount of light from, let's say these are two 6-inch mirrors.
Yeah.
You're combining those images by the distance between them. So I don't see how you're going to get, like, say, a 12-foot mirror.
Yeah.
Don't confuse light collecting power with resolution. They're two different issues.
Yeah.
Oh,
The resolution has to do with the separation of the two mirrors. The light gathering power is the diameter of the two mirrors that you have.
okay.
Area,
I
surface
think
area.
that's where I'm confused. Okay.
Right, Tim, a 12-inch mirror give you 4 times as much light as a 6.
Right, right.
Tim,
Okay.
think of
Twice
it as though
resolution.
you took your 14-foot mirror, but you only had a 2 spots on it that were illuminized, and one of them was on one side and one was on the other. So you'd get the resolution as though you had that great big mirror, but you're only collecting the 2 6 inches worth of light.
Okay. That's
Yeah.
kind of where I was confused. So,
And
Now
okay.
this
Tim, while
image
you're on it,
this image
because
down
Tim,
here.
while you're on it, imagine how much time it'd take you to figure a 14-foot mirror.
Yeah. Yeah. I was also thinking about how they collimated that scope with all the multi mirrors on it. That I was thinking, the James Webb.
Mm.
It took them time to collimate that, and I'm wondering how that collimation would work on these.
We're gonna have to visit this again.
Collimation is key.
Yeah, it's really good.
This is this image down here is an image generated of the star Polaris using
Okay.
this technique that you see here.
Okay.
This is a constructed image and constructed 1 point at a time using this technique.
Wow.
Interferometry.
Mhm.
Yeah. And I
That's
think that's the
fascinating.
limit of our time for today.
Okay.
We've gone over, but man, I tell you, I'm still grasping him and as confused as Mr. Crawford is. Well, gents, let's do this again. Let's continue next week. By golly, April 21st for our 216th will be next week. And I'll quote 2 people here in my close. Casey Kasem used to end his American Top 10 program every week with, "Keep your feet on the ground and keep reaching for the stars."
Okay.
And then our outreach guy says, "Hasta Nebula." Till next time.
Yeah.
Thank
Thank you,
That's it.
Ronnie.
All right,
Okay.
my friends.
Bye,
Thanks,
guys.
Next
everybody.
week. Take care.
Goodbye, everybody.
Bye-bye, Jerry.
Bye.
Thank you.
Whee! Dive, take her down to 300 feet.
They go a lot deeper than that.
Little X on the screen at the upper right. Leave the meeting.
Oh, no, it says live on mine. Get my pointer here. Well, I can still see Tom.
Yeah, I see you.
Where's the little, I just do this. I just turn it off. No, I just put it in the background. Oh, there, finally it shut off. No, it didn't. What the hell's going on here?